It seems strange that it could get to 3 and can't go anywhere else.
So let me explain a little bit of why that's true, but also why this is an interesting and hard problem. So let's just use the example of solving the original, like there's only one thing. Trying to find Z and C, which have this property, right? Because remember, both of them were changing, right? I had to choose a C and choose a Z so that I could find a cycle like this, a periodic point like this. For Z maps to Z squared plus C, to say that a point comes back to itself when we iterate it is the same thing as saying that Z is equal to Z squared plus C, right? Now, if these things are fractions, so let's write them like that. Let's say Z is M over N, and let's say C is, let's use K over N. I'm going to assume they have the same denominator. I can do that just by making them in common, right? Then what is this equation equal? It's saying that M over N is equal to M squared over N squared plus K over N. Okay, let's multiply out my N's. And what this is telling me is that if I can find numbers Z and C which do this, then I can find integers M, N, and K which satisfy some polynomial relationship. Asking for integers to satisfy a polynomial relationship is a really hard question to answer, right? Like Fermat's last theorem is the question of finding integers which satisfy the polynomial relationship that, like, say, x to the n plus y to the n equals z to the n. And so that's why the question is hard. The reason why you might expect that we can do it if n is really small, so if we only have one number or two numbers or three numbers in the cycle, is the same reason why Fermat's last theorem doesn't hold when we're squaring the numbers, right? So we do have infinitely many, say, x, y, and z, so that x squared plus y squared equals z squared, these Pythagorean triples. But once the exponent gets higher and higher, it's harder and harder to solve that equation. And the same thing is true here. If you try and reproduce this calculation that I did, when you're looking at coming back to yourself after 2 iterations or coming back to yourself after 3 iterations, you get some polynomial which is more and more complicated. And so first of all, harder to figure out if it has a solution, and second of all, less likely to have one.
Oh, that's cool. I love that problem.
Yeah, me too. I mean, it's so like simple to state. And the fact that we just don't know, I mean, I get frustrated by that fact. But I think it's really interesting about like sort of what is a hard problem in mathematics. Because sometimes there's this, idea that the easier it is to write down a problem, the harder it is to actually prove it. And this, I think, is exactly an example of that.
Is this like one of the big problems in your area, or is it like a trivial one?
Yeah. So it's called the uniform boundedness conjecture in my field, which is quite a official and big sounding name, right? And it was asked, I don't know, maybe 20 or 30 years ago, and people have worked on it since then, but not with a lot of progress.
Are you working on it?
Oh, I couldn't tell you that.
Let's have a look here.
I hid all those papers, don't worry. And in fact there is. It turns out that that's the 2/5 of the way around the circle, Ray. And the point is that under this stretching map,